Hello, today I'm going to show you guys how to calculate the surface area of a certain graph, y equal to fx surrounding around a certain axis. And in general, we have the function y in terms of x surrounding the x-axis, and let's say we have some arbitrary continuous and differentiable function from a to b. And we have that graph of that function surrounded or circulate the x-axis and created some surface. And we're going to use calculus to calculate what is the value of that surface, the surface area. So from A to B, we know that the graph is surrounded or circulated around the x-axis. For some values of x, let's say a sub y and a sub y, a sub I and a sub I plus 1, it's continuous, right? So there's a value corresponding to each x value. There's a y value corresponding to each x values. So we're going to pick a small increment, a small fragment of the surface. So when we extract this thing out, this surface out, we're going to have in this shape, right? And what's it called? It's going to look somewhat like a trapezoid, but it's like a cone but without a top. So what we call that, there's a term for that called the fruit stump. So why is it that it has a straight line like this, or why is it not? It has some curly things like that, and then you could have something like this. But we pick a value x, right? The increment is small enough so that the delta r, the length here we have is almost like a straight line. So we have a fruit stump instead of some we are looking surface like this. And here's the fruit stump, but it doesn't have any things inside, so it remains at the surface. So it doesn't have any volume. Well, it can have a volume, but what we're interested in is the surface, right? The area surface of this thing. So how do we go ahead and formalize this areas and go about give it a general equation whenever we want to calculate the area of a certain graph surrounding a certain coordinate axis. So let's go ahead and have a look at this fruit stump. So we know that this is delta r. This thing right here is delta r. And as soon as we pick delta r such that as r small enough so that this line is almost like a straight line, we can go ahead and have a top view of it. So the top view of it will look something like this, right? Right? Like a shape of a donut, you can think of it like that. So this is delta r. Okay? So now, since it's a delta r can reach to some value. We can set so-called the limit of delta r. So delta r, when delta r get really small, you can think of this like a strip, right? This thing turned into a really thin and finite strip. So it gets smaller and smaller. The strip gets smaller and smaller. Almost to the point that you can imagine that this strip, you can cut it at some point along this strip, and you can cut it so that you would have something like this. You have some shape that look like this. Right? So when you have this strip, and what we're interested in is the area of this strip. So what is that area? Well, is this the remaining delta r, right? And since this strip is too thin, that we wouldn't carry much about the difference of the delta y, right? So we can say, let's take this as a center, right? Since it's a circular rotation, so there's always a center. So we pick a center right here, and this thing is just some value. We see here, we put it in the top view, therefore this view will be y, right? So it will be some y sub I values. So then we have some general form. When this fruit string get really small, we would have the area is almost equal to 2 pi y times delta r. Okay? Area equal to 2 pi times y times delta r. And this is some value y sub I. Okay? Alright. So now we're gonna go ahead and expand on that. What do we have next? So we can think of this whole surface is the sums of many strips. We cut in segments, really thin strips like this, and then we're going to calculate the areas. So we had before the area of one strip, a sub I, right, is almost equal to 2 pi y sub I delta r. Okay? Now we think of it as the sum of really thin strips, so the A of the big A, right, the A total of this entire surface circling around x-axis would be almost equal to the sum, start from I, go to n, go to some n, 2 pi times y sub I delta r, I maybe. Okay, so there you have it. But the thing is, we don't stay at the estimation. We want some concrete values and some definite values. So we're going to put the limit on it. What happened to n as n approaches infinity, and what happened to delta r as delta r approaches 0? Because we want this to be very small, as small increments that we can get. So therefore we can have some the A total be equal to the limit as delta r I get to 0, and the sum of it start from I and go to infinity. N could be any n, as big as n can get. That's how many. The more n you get, the more strips you dissect the surface into many thin strips, the more accurate the value of the surface area going to be. But we don't have like a there's no such thing as the best value for n. It's the only thing that the infinity is what we have in order to formalize the situation. So I goes from some values, let's say 1 go to infinity, and 2 pi e sub y some delta I. Why is it 2 pi here? Because in the beginning we talked about this, right? The thin strip, we can think of it as just a circle, right? And we have to, it's like when you cut the strip, right? And you cut the strip and you expand it out like that, you open it up, it almost looks something like this, right? It has that was not quite. Right? So this thing is almost like when you calculate the length of a curve, right? So this thing, when you have a circle, so the circumference of a circle is 2 pi I, right? But there's a width, and that width is just delta r, so that's why we got it times by delta r. So that's why it's, each strip like that is 2 pi y sub I times delta r sub I. So it happens when you turn this infrastrum into a really thin, very thin strip. So now you have it. So how you put it in an integral form, we have this formalization of the integral form. So then we have it, this is the integral of 2 pi I times dr, okay? And r go from some value to some value. But the thing is, we don't have a function for r. R is just a symbol for us to annotate the length of each the length of the side of the frustum, right? How long are we going to get? How long are we going to dissect the surface area into small frustum? So that is dr. So how do we change dr into something that is more manageable? Now we know that delta r, when we get really small, so we can say delta r small is almost equal to the let's just say dr small enough so that it's straight, okay? So that it becomes a straight line. So dr small enough to have it equal to the equal to delta x squared plus delta y squared together under the square root, because you apply the Pythagorean theorem. Okay, so there you go to that. And how do we transform this into this? And we can transform it into some general equation. So we have a equal to integral 2 pi y. Dr becomes the square root of dx squared plus dy squared. Okay? Now, since we have y is the function f of x, so y is in terms of x, so we can do something about this. We can somehow transform this and make this integrals in terms of d of x, because y is a function of x. So we can do something like this. We can see we have dx, so we can pull the dx out. Dx squared under the square root of that dx, so we can pull out the dx squared. When you pull out the dx squared, right, this becomes dx squared over dx squared is 1. Okay. Dy squared over dx squared is y prime of x together square. And since we pull out the dx squared but under the square root, therefore it's only dx. Okay, so this is the and x go from a to b. So this is the equation for the areas of a certain function y equal to f of x surrounding, let's say, x axis, and therefore the area values for this rotation a equal to integral a from b 2 pi y times the square root 1 plus y prime x squared times dx. So that is our equation. So